All right, we're going to go ahead and get started because I want to give each of the speakers their full 20 minutes. You do have a full biography in the program, so I'm not going to read that whole thing. I'd rather give the time to the speakers. Since I know two of them pretty well, I will throw out a little bit of a fun fact. In Tyler Lay's biography, it does not mention the fact that he is a Regents Professor at Oklahoma State University, which is a really big deal because there have only been 3 in the entire history of the Department of Civil and Environmental Engineering. So please join me in welcoming Tyler.
All right, let's see if I can walk and talk, and you still film me in the back if I walk and talk. Is that okay? My slides, are they up and running? It is always excited to be in this group. Let's see, moving. There we go. Hold on now. There we go. All right. How about if I just drive? Is that okay? There we go. Oh, great. So that's my talk. Let's get started. How many of you would like to do more with less? Does anyone want to do more with less? Yeah? A few people in here. How many of you would want to build infrastructure to improve people's lives? You up with that? Give me a yes. Yeah. How many of you want to build long-lasting infrastructure? Infrastructure that can last for generations. How many of you want to do that? You down with that? Now I'm going to ask you, do we know how to do this? Do we know how to do this? I think we do. Do we know what to do? I think we do. Well, then why can't we do it like day in and day out, over and over and over again? I think there's a really, really, really good reason for this. There's 3. It comes to time, it comes to money, and it comes to people. And if you think real hard about your problems, I bet it comes down to one of these 3 things, or maybe all 3 of these things. And I'm going to be talking about these 3 things today, and how we can address them with concrete construction by using 3D printing. Who's heard of 3D printing? Anybody heard of 3D printing in here? Yeah, here's a headline that says 3D printing promises to transform architecture forever and create forms that'll blow today's buildings out of the water. I'll tell you, when I first heard this, I thought, man, that sounds like a bunch of hype. But I'll tell you, I've been working on it for the last 7 years. And ladies and gentlemen, it is not a matter of if. It is only a matter of when this technology becomes commonplace. And maybe, just maybe, by the end of my talk today, you might feel the same way. And if you don't, that's fine. We can talk afterwards. Let's get started. You know who this is? Come on, you don't know, come on. Civil engineers, you know who this is? Edison, baby, inventor of the light bulb. Edison also, inventor of the phonograph. Edison was actually instrumental in developing the motion picture camera, syncing sight and sound together. Pretty awesome. But did you know more than 1/3 of Thomas Edison's patents were about cement and concrete? Did you know that? Did you know that Thomas Edison owned his own Portland cement company? Did you know the first concrete roads were built with his cement? Yankee Stadium was built with his cement, but Edison's dream was a concrete home. Here's a picture of it in 1919. And here's a picture of it being built. Look at that formwork. Pretty intense, right? Pretty awesome. Pretty crazy. Well, Edison built about 100 of these, and more than 95% of them are still in use today, about 100 years later. It's pretty awesome, right? Pretty amazing. But Edison's benefits, this is what his marketing terms were. He said, I'm going to build you an insect-proof, a mold-resistant, a home that does not rot, a home that's fireproof, a home that's designed for extreme events, a structure that will outlive the builder. But I'll tell you, Edison got that last one wrong. Didn't just outlive the builder, it outlived the builder and the builder's kids and the builder's grandkids and who knows what else. And that's the potential that's out there with well-built infrastructure. And that's why people build concrete homes now. Not everywhere, but certain places people build concrete homes. Now, 3D printing is pretty cool because you don't need much of that formwork. Remember all that formwork I showed you earlier? Pretty complicated, pretty crazy, right? You don't need any of that. Goes away. There's labor savings involved as well. There's faster delivery. There's less waste. There's so many benefits. And people love to say, you're going to get all the benefits of concrete with X% reduction in price. It's like, what is this professor doing? Put an X up there. What's the number? How much money is it going to save me? And people honestly don't know right now. They don't know how much money 3D printing is going to save them. But actually, today, with modern techniques that most folks use, 3D printing is more expensive than conventional construction. And so they're like, well, why would I ever do it then? And you're right. That's why it's not everywhere. But get ready. Get ready. But I think long term, X is going to be about 30. So about 30%. So imagine buying a home, but it was 30% less expensive. Imagine your mortgage payment that was 30% lower per month. Could you find something good to do with that money? Could you find something good to do with that money? I know I could. I could definitely find something good to do with that money, and I bet you could too. And a lot of other people in the audience could as well. And this is what 3D printing currently looks like. There's these columns, there's this gantry system above, and there's this nozzle. We're going to zoom in on that nozzle and see what's going on. That's where the concrete comes out. Well, concrete? Is it really concrete? Does anyone see any rocks in that? Do you see a rock in that? Come on, geotechs. Do you see any rocks in there? No, the geotechs, they don't want me to talk to them. But there you go. There's no rocks in there. There's sand, cement, and water. That's mortar, okay? That's in there. That's not really concrete. That's mortar, but that's what people are printing with today, right? And they look like this. Who thinks this is beautiful? I have yet to find, we got two people, right? Most people do not think it's beautiful. A few people do, okay? But they usually print these cavities inside their concrete walls. And inside those cavities, then they put in rebar. See, rebar in there. Wow, man, this thing is not doing very well. They place rebar in there, then they fill those with concrete, and that's a lot of steps for 3D printing these days. A lot of steps. So gantry printers, these overhead printers are expensive. Most are around $3 million, all right? They print with mortar. Mortar's more expensive, less durable, less sustainable than concrete, and it costs more than conventional construction right now. It does, and that's why it's not widespread. But now let's go back to 2017 for a second. Go back in time, see what's going on. This is Paul Tukowski. He is my boss's boss. My boss is over there, but he's my boss's boss, right? And he sends me an email one cold December morning. I'll never forget it. He says, hey, come and see me. And I'm walking across campus, and I'm walking across campus, I'm breathing. You know those cold Oklahoma mornings where you can see your breath, right? You can see your breath. It's that cold outside. I come walking, I get into his office, I take my coat off, I start to talk to him, say, hey, Paul, what's going on? He says, Tyler, I need a favor. That's never good when your boss's boss asks for a favor. And then he said, I need you to do something that you've never done before. Oh, man, I was 0 for 2. All right? And I felt in that moment that the room had just dropped 40 degrees in temperature. I felt like I could see my breath again in front of my face. It was amazing. It was crazy. It was chilled to the bone what's going on. I said, well, sure, Paul, because this is a visionary guy. This is a guy I look up to. I said, how can I help? What's going on? He's like, our engineers today and our architects and our technologists are very focused on what they do. And they need to learn how to work in teams, how to work on multidiscipline problems, because the world's problems are solved by teams. And we don't just do one thing, we do multiple things together. You guys ever noticed that before? Anybody ever noticed that before? Geotechs, no, they don't know that. Everyone else, though? Yeah? You seen that before? Excellent. Well, that's awesome, because that's what he saw too. And he said, we need to facilitate that by teaching a new senior design class where somebody teaches all these different disciplines. I was like, well, who's going to teach it? And he's like, yeah, you are. I was like, oh. And I was like, well, what problem am I going to solve? He's like, well, it got to be a big problem, a huge problem, because a huge problem is how you get everyone rallied around together to solve something big and strong, something that's bigger than themselves. I was like, well, what's the problem? He's like, I don't know. You got to figure it out. And I said, oh, crap. What am I going to do? And I got really, really scared, but I'll be honest with you. There was a part of me that was excited. There was a part of me that was excited because he was asking me to step up and doing something big. And I hope every one of you will reach inside of you and try to find that exciting part of you, all right? And embrace that throughout today and throughout this presentation. And so I said, why don't we do 3D printing? So I said, let's do 3D printing one-story economical homes. And I taught this class for 6 semesters, 63 different students, 6 different disciplines, mechanicals, electricals, civils, architectural engineers, architects, industrials, all working together, right? We built 4 working 3D printers. Now, 3 of them didn't work very well, but baby, you only need 1. You only got to have 1. That's what's important. We trial batched more than 100 different concrete mixtures, okay? We did grout mixtures, and then we did concrete, real concrete that has aggregate inside of it, all right? We worked on all this stuff, the concrete, the equipment, the architecture, the construction, the automation, every bit of it, but everything, ladies and gentlemen, starts with the concrete. Because if you don't got the concrete, you got nothing when it comes to 3D printing. So let's talk about that concrete. What is the goal of 3D printing concrete? We want concrete that flows under energy and then stops as soon as that energy is actually taken away. And this, ladies and gentlemen, is called thixotropy. Ooh, that's the science word of the day, thixotropy. And if you don't know what I'm talking about, it's ketchup, ladies and gentlemen. We're making concrete that acts like ketchup. We actually studied ketchup intensely on why ketchup works, what ketchup is all about. Very, 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 very big thing, all right? So we make our concrete do this. But our concrete, we use 1-inch maximum nominal size aggregate. So large rocks, all right? Our concrete 6,500 PSI compressive strength at 7 days. We're not designing for that high strength that comes along for the ride. We use a 0.45 water cement ratio. Our mix is about 5% more costly than a typical mix. And we do this with aggregate packing, with powder packing. We use physical methods to create that thixotropy. Now, I'm not saying I don't use any admixtures at all. We do. Admixtures are important, all right? But we do it with physical methods. Because if you rely on chemistry for everything, then you're gonna have non-robust mixes in the field. So we'll rely on physical methods, right? So let's talk about how this works. So notice that thing in orange there. That's our pad we're going to drive on. Okay, and that pad needs to be level. Doesn't need to be made out of concrete, although it'd be amazing if it was. It can be anything, just stabilized soil, something level. Then we have a footing, and does everyone see the rebar sticking up out? Does that make sense what I'm saying? Rebar. We print around rebar, ladies and gentlemen. All right? All right. So we have this cartoon here, right? This cartoon, it's got a hopper. The concrete goes in the hopper. We have an auger in the bottom that spits the concrete out. We have an arm that goes up and over the rebar and catches it on the other side. So everything happens in that box. It smooths it. It consolidates it. It finishes it. It gives us its form. It does everything. That box is magical, and I'm going to show you all about it coming up. This is what it looks like. So we see the hopper on the right. You see this extruding nozzle at the bottom, which I'll talk about in just a second. You see the magical box, and does everyone see that little tractor in the back? See the little white tractor in the back? Because, ladies and gentlemen, that's a skid steer or a tractor. And what we like to say at Oklahoma State is if you can rent a tractor, then you can print a house or a wall or a bridge or whatever. And I've already seen it in the faces. What? Really? Yeah, hold on to your horses, ladies and gentlemen. Now, in that nozzle itself, right there, what's in there? That in there is very important. There's an auger in there. If you don't know what an auger is, it's a screw that spins, that pushes material from one side to another, right? Pushes it, pushes it, pushes it, right? And this thing is called the BAM printer, because you got to have a sweet name, right? And BAM, like you get to say BAM to everybody. And BAM stands for the box auger method printer, because the box is really important and the auger is super important as well. So let's jump in. So there is the BAM getting all lined up there. Rebar's already in place. The only formwork we have is at the very beginning and at the very end, right? And then there's the auger. There's everything lined up right there. And let's look at this box. This box is magical. So many cool things happen in this box. So let's look inside of it. Now there are 6 flaps to this box, 2 in the front and 4 on top. They all have hinges, so they can open and close again and again and again. So you can open it up if you want to get in the box, or you can close it down because it will consolidate inside that box, and I'll prove that to you coming up. Now on the side there, we actually spit concrete out from the side. We have an auger that spits it through the wall. So most people print from the top. We print from the side. It's really important because we can print around rebar that way. See the rebar? We're going to print around the rebar on the structure. Still don't believe me. I get it. Here's the box. Everything's closed down. See the rebar coming out there? Let's keep an eye on it. See the concrete? See the concrete? As soon as the concrete comes out of the top, as soon as it squeezes out of the top, you drive forward, ladies and gentlemen. And as long as it's squeezing out of the top, you know you are consolidating, you know you're getting the shape, you know you're getting the form, and it goes again and again and again and again. And there it is, the same box from the other angle. That was the back, this is the front. Look at the concrete. You see it kind of creeping out of the front like ketchup? There it is, creeping out, creeping out. As long as it's creeping out of the front, you're good. You're getting the consolidation, you're getting the form, you're getting everything you want. Pretty awesome, pretty simple. And we just do layer upon layer upon layer. And people love to ask all the time, well, how long do you have to wait between layers? And the answer used to be about 30 to 45 minutes. But we have a new technology I can't tell you about yet that you don't have to wait at all. You don't have to wait at all. You can print immediately on top of one another again and again. You can back printers up. If you want to have 3 printers back to back to back to back, you can print again and again. And we print 8 inches wide and 8 inches tall. 8 inches wide, 8 inches tall. Now, if the concrete is perfect, then we can do 16 inches tall, but it's tough to get perfect concrete in the field. If we're making it in the lab, not a problem, but in the field, it's a little more challenging. So here we go. Oh, look at that. Look at that truck. Do you see that name on the side? That's a great company, DeLisi. Thank you, DeLisi, for all your help that you've given us on this project. I appreciate you. Right? We did this with ready-mix concrete, local ready-mix concrete produced in Stillwater, Oklahoma. And there is one of our prints. Now look at that left-hand side. Isn't that looking good? Man, that's looking good. Well, what's going on the right-hand side? Well, one of our hinges broke, so we had to have a human pack it down. Just keep printing. But look at that left-hand side. Looking good. That's 2022. Okay? Here is the middle-of-the-road mix. Not the best mix, not the worst mix. And I'm having... There we go. Problems. 2022. We can see some surface voids. Now, one thing that's cool about this mix is you can finish it and fix it right there. If there's any problems, you just fix it up. Whatever you want, right there. Pretty cool, right? Now, here is 2024. This is about 2 weeks ago. Much, much better. We've come a long way in our mix in the last 2 years. Here's the other angle. Okay, pretty cool. You can do other cool stuff with this concrete, like this is me, and then you can just carve in it. That's 30-minute-old concrete. I carve into it about 3 inches and do an 8-inch wide thing. Carve into it 3 inches. Doesn't collapse, nothing wrong, and I can patch it up immediately. Now, architectural folks, okay, I don't know if there's any architects in the room, amusement parks have seen this, and they're like, holy cow. You know what I can do with this? They want to like carve murals and stuff, and I can't wait. Can't wait. See like the Oklahoma land run carved in a concrete wall? Oh man, let's make that happen, right? Now here's another cool thing. Here's me kind of pushing, and what I end up doing is I take my entire trowel, my hand tool, and I just poked it entirely to the wall. And then there it is. There's my hand. Doesn't collapse. And then I patch it up. Oh. I just patch it and finish it. This is a different kind of concrete, ladies and gentlemen. This is a different kind of concrete. Crazy, right? We printed a building, 2022. Pretty cool, 8-foot high walls, right? We printed a 30-foot by 20-foot building, 8-foot high walls. We did it in 14 hours. With $2,000 of rented equipment, $4,500 of concrete, okay, $6,500 total. We used 4 students, ladies and gentlemen, 2 high school students, 2 college students, no construction experience, okay? The person that drove the skid steer had never driven a skid steer till the week before. This is not an experienced group of people, ladies and gentlemen, that are able to do this, but our students are amazing, all right? This building is a research storage equipment facility for 2 environmental engineering faculty members. We improved our designs, we filed 2 new patents, but we got real world costs. That's big time. Our 3D printed wall, now this is for an 8-inch thick concrete wall, 8-foot high with typical labor, not my student labor. I took how much time it took each one of the students to do all the work, took out their cost per hour, put in typical labor cost per hour, $12 per square foot. You're like, well, that sounds cool and all. How does that compare to real world stuff? There's real world stuff from a general contractor for cost. 8-inch thick concrete walls, $55 a square foot. That's their cost in place. There is CMU, there is 6-inch 18 gauge stud. That's a 4.5 times reduction in cost. That's a 4.5 times reduction in cost. All right? So where does this system excel? Where's this awesome? Well, housing, this could be great. Agricultural structures, any place you want to use block wall, this could be amazing. Retaining walls, this is slick for retaining walls. A lot of work on retaining walls. Box culvert bridges, talking to ODOT now about building box culvert bridges using this technology, right? Water tanks, this is awesome. And then there's a new project, ladies and gentlemen, we're working on with underwater concrete. Man, everything is just underwater concrete jumping around, which is really cool. So what are the drawbacks to the BAM? Well, you got to have a level path, and you can only print as high as your vehicle can lift. And you need to work with a company that knows how to create 3D printable concrete. Thank you, Delisi. I'm glad you exist. All right. You need to be able to adjust concrete in the field. That's a big deal, and it is not automated yet. Right? We're working with Bobcat now where we can actually control our entire thing with our phones. We can hook this up to a video game controller. The students loved it, or at least we're in the process of doing that. And it's like playing concrete video games, right? Pretty awesome, right? But we're actually doing this in the lab. There's no driver, ladies and gentlemen. There's no driver. So you remember the 4 folks I had before? I could easily do that building now with 2 if everything was perfect. But in construction, not everything's perfect. So 3 is probably where you need to be. But what's next? Make everything better. Add automation. Get the feedback from industry. That's a big deal. So, hey, do you know someone that'd be interested in this? That's my big call to action. Do you know anybody that would think this is cool? Do you want to come see it in action? Do you want to come see our building that we've made? You can email me, talk to me. So in summary, 3D printing with a tractor is shortened our construction time of this building by about 7x, reduced our cost by 4x, reduced our number of workers by 2x. Those are the 3 big challenges that I said were facing us today. This is a way to attack all 3 of those in what we do. And this is all compared to conventional cast-in-place construction. So listen, this has been a cool day. I always love coming to this event. And listen to me right now. If you're at this event, then there's a little piece of you that wants to make the world a better place. And for this quote, oh my gosh, what is this? This quote is for you. It's not easy. It's easy to say, it's not my community, not my world, not my problem. Then there are those people who see a need and respond. And I consider those people my heroes. And if you're here today, you are one of those people, and you are one of my heroes. Thank you so much. I appreciate you. Take care.
We don't really have time for questions, but you know where to find Tyler, I hope. So our next speaker is Bryce Hanlon, the geotechnical engineer for ODOT. And I'm sorry, I don't have any fun facts for you, so you got to come up with your own. Thank you. Welcome, Bryce.
Okay, can you guys hear me? Okay, I'm going to try to liven this up a little bit after that presentation. So let's talk about some geotech. All right, like you said, my name is Bryce Hanlon. I'm the design geotech engineer at ODOT. It's been exciting. I worked in consulting for a long time in Oklahoma, so kind of coming over to the ODOT side, seeing what's going on there, trying to improve the processes is kind of what I've been doing. So let me try to figure this out. Yep, there we go. So what I'm going to talk about the changes that are happening in ODOT. There's a lot happening, not just in geotech, but I'm going to focus on the geotech side of it. Talk about a GIS map that Scott's group in materials has been putting together and the benefit of that and how it's going to help the geotech industry going forward. And then talk about geosynthetics for pavements. It's a big topic. Let me just grab this. It's a big topic that has been brought up ever since I started, and we're going to talk about how we're going to implement the geosynthetics, get the most that we can out of them, and hopefully save money in the long run. And then talk about future goals. This is only a 15-minute presentation. I'm going to keep everything very surface level, but talk about future goals with ODOT when it comes to geotech and improvements we see making, and then I'll hopefully answer a couple questions at the end. Hold on. There we go. All right. So the geotech group at ODOT, I started about 18 months ago now, and I'm the design geotech engineer. The job didn't exist before that, so they kind of put me as a kind of a central figure to coordinate between the geotech consultants that we rely on, and then Scott, who manages the materials group, and then the pavement design engineers that work in the roadway division and the bridge division's geotech engineer. So I'm kind of the central source. I help a lot with processes and helping them kind of, if they do need some technical help. For the most part, they have their technical stuff figured out. But my main role is to help be the central contact with the consultants and help them to understand kind of what the expectations are from ODOT, get the processes that they're following to be consistent from company to company. Yeah, and basically trying to be a central point of contact. Kind of before ODOT had all these different people that they could, contact, but they didn't know who to contact sometimes, all that. So for geotech, I'm kind of the main deal, and then if I obviously would reach out to Scott or Amanda with payment design if they need more technical help. So changes happening at ODOT. Consultants. So we've grown a lot more reliant on them in the last couple decades. So I would say like 2000. Chris Clark. ODOT did the majority of the geotech kind of. We say up to like 2000-ish. Okay. So for the most part, ODOT did all the geotech in-house for a long time, and then they have grown to just with the amount of workload and just kind of the just how the the personnel has gone. The consultants have kind of taken on more and more of that task as we've gone. So as they've taken on more of a role, we've obviously grown dependent on them. So we need to take care of them. So one of my first things I had to do whenever I showed up was update kind of how invoicing is done and how we pay the geotechs and the methods they use to get paid and all this stuff. It was very outdated. A lot of it, I think, was put together by non-geotech people, kind of not understanding all the intricacies of the project. So last year we had a lot of meetings with the consultants, and we figured out what gaps there were, and we worked towards not only updating the fee schedules, but the fees. We did kind of like an industry calibration where we feel like all of our rates now are up to what the industry standards are. We're allowing the engineers to be able to bill their time according to their engineer hourly rate. Before, it was an established rate that they had to use. It's just a lot of stuff that's kind of bringing the geotech industry up to where all the design groups were. We were kind of felt like we were being left behind. So I think we've done a good job getting that to where it's up to date, and then it'll be sustainable going forward. We are working on a geotech manual, which is, it's a pretty big deal. We for non-geotech people at ODOT, they get these reports, and I feel like a lot of times they have no idea what's going on in there. Like they'll have like maybe one design parameter they're looking for, but they don't really know how to interpret all the information. We developed this manual to where they can kind of have a quick go-to reference to if they read something in a report and they want to know what that means, they can go to that. And the manual is directed strictly towards ODOT projects, so bridges, retaining walls, roadways, that kind of stuff. So I think it's more of just like the spreading the word about geotech, like what does this information mean? How can you use it? How can you apply it? That kind of stuff. And then we are just modernizing. I mean, geotech processes, how would I say, like geotech is kind of an industry that has remained relatively unchanged, I would say, for a while. A lot of the test methods are very, they haven't changed a lot in decades. So we're looking to modernize at least how we interpret that data, how we store that data, how we use it in the future. And then kind of as we go along, obviously get the consultants on board to where they understand the expectations and the processes and the formatting that needs to be used going forward. Let's see if I get this to work again, hold on. All right, GIS map. So this is Scott's group has been working on this since I showed up, and this is going to be a super cool tool going forward. I mean, this is something I'm hoping that it'll be used for decades, generations to come. So geotech data, obviously, you're working with soils and you're working with bedrock information that it's not changing all that much. The soil kind of is what it is in an area. The bedrock elevation isn't changing over time. ODOT has a lot of data. I mean, so much data. I think it's been mentioned a lot today, but using that data to improve our processes going forward and not allowing us to have to pay for the same service over and over again at a similar location is kind of what we're striving for. So Scott's group had these boxes. How many boxes do you think you had, Scott? Just filing, yeah, just. So the old geotech submittal format was just a hard copy of a bound report up until about maybe 15 years ago. Since then, it's been all PDF, but before that, for decades was just a hard copy. And they'd send some to ODOT, and they would just, after they were used for that particular project, they would go into a box. Obviously copies were made and stuff, but they would go into a box and stored. Well, all this information is good information. There's good soil information in there. There's good, a lot of stuff. I mean, you can get groundwater information, all this stuff. And potentially that stuff could have just got thrown away, never to be seen again, but kind of the direction we're going is like, hey, this is good information. Let's not lose history. Let's scan it all, which Scott's group and Chris has been doing this for a while, but they've been scanning all this information, saving it into a GIS database to where it's going to be searchable, usable, not just for ODOT, but for the consultants going forward. So I'm a big history person. I hate the idea of doing all this geotech work and it just be basically set on fire, never to be used again. Like having your information potentially used 60 years down the line, I think is pretty cool. People looking at all that work. From what I can tell, I looked at it the other day, that they've been working on it a lot, but they've worked mainly on the older scan documents up to about 2013. So they have, what is that, about 50 plus, 60 plus years of data that they've starting to get in there. They're working basically county by county, getting all that information in there. And then obviously since 2013, a lot of it has been more of a digital format. So they're going to be adding that as we go. It'll be a lot easier to add stuff that's already in the right format. A lot of it is scanning and deciphering what information is in these reports and being able to catalog everything. Oh, jeez. All right, so benefits of this. Why are we doing all this? I mean, the big thing, like I said, history is important. Saving this information, I think, is important. But being able to use the data to more accurately scope projects in the future and potentially deflate budgeting. Obviously, ODOT only has so much money every year to spend on projects. So the idea is the most information you can have to be able to budget a project, the more accurate you can be with your budgeting, thus leaving potentially more money down the line to use on other projects. So a good example would be like, bedrock, obviously. A lot of times whenever you budget a project for geotech, you have to estimate drilling costs, time for your engineer on site. If you don't know how deep the rock is, you assume a crazy high number, because if you don't have enough money, you have to ask for supplemental, and that's a whole problem. So, making sure you have enough money in there is good, but you need to make sure that it's also not just crazy high numbers. So, being able to more accurately scope projects, being able to identify potential problem soils on a project. So if you did a report 20, 30 years ago in an area for a roadway and you saw that there are sulfates in that area, or there's shallow rock, or there's shallow groundwater, like all these things that could potentially cause pavement issues, being able to identify before you show up, maybe, increase your testing in that situation. Be like, hey, this was a problem before, the road obviously was designed a certain way. We need to make sure that these conditions are captured in our study, that kind of stuff. And then, like I said, reduce the quantity of drilling and lab testing eventually, I think would be ideal. Right now, we treat every project like we've never been there before. So we have a kind of a set scope that everyone follows, and it's the amount of borings based on the amount of foundation elements like a bridge has, or how long a roadway is. Now, if we can basically add this other variable, like, hey, we have existing information, why don't we trim this back a little bit? I think it'll be helpful. Obviously, it'll save us money, but we'll actually have, in actuality, more information. Like, we'll have all this old information, plus some supplemental information that they get going forward. And like I said, the big thing, I think having this just as a resource, it is going to be publicly available eventually. I don't think there's a lot of states that have this kind of information publicly available. So just having this kind of stuff available for like the universities to use, for obviously DOT to use, the consultants to use, it's going to be a great resource. So here's an example of what they've put together. You can see how a GIS map works. This is kind of the default thing whenever you log in. The red is basically every project that has a geotech report or geotechnical data tied to it. So they've made it super searchable. I would have killed for this as a geotech consultant, just having this much information available. But you can obviously search by county, JP number, the year the report was done, all these different types of reports. There's the pedologicals, bridges, all these things. You'll be able to search it, find information, try to find stuff that applies to the project you're scoping. It's gonna be great whenever it's all done. So for this presentation, I just showed you an example of what it can do. I've just picked Oklahoma County because where we're at. So what you do is you click Oklahoma County, it zooms into the county, shows you all the projects within that county. And then say you want to see an example of like a pedological report. Oh, if I can get the thing to work, hold on. Maybe, no. So say you want to get a pedological report, it'll zoom in and just show you where the red is, where the pedologicals are. So you can see there's probably about 7, 8 pedological reports for the county that have been stored in the system. And say, hey, I have a project maybe like in Arcadia on Route 66. What's the soil information like over there? You can basically, it'll highlight that once you click on the red. It'll show you the report that you have, which I didn't go through showing all that, but you can get the report from there. You get the JP number assigned with the project that the study was done before. With that, you can potentially ask for as-built plans. You can get all this information that was done previously, and you're not basically starting from scratch as a geotech, which is a lot of times I felt like that. But yes, having additional information makes you be able to make more educated plans, more educated scoping plans, and obviously help the project as a whole go better. So I'm going to reiterate, kind of the end goal of this is obviously eventually to save ODOT money by not doing redundant testing and drilling, allow the geotech consultants to provide reduced scopes and more accurate budgets, and then creating this digital library. I love the idea of having a geotechnical library for ODOT stuff. This can be be continued for 100 years, and you'll have all this data from the 1950s all the way up to what we're doing now. Yeah, I think it's going to be very helpful. And then eventually, like with AI, maybe there'll be a way we can search this, and you can have some sort of system in place where you can look up these old reports and get data from that. That's out of my league, obviously. I'm a geotech engineer. I don't deal with AI very much, but yeah, I think it'll be useful. Okay. So geosynthetics for payments. This is a big topic that has been brought up, like I said, since I started. Geosynthetics, the main purpose they serve in a pavement situation is they will either provide separation of the base layer with the soil, filtration with water, and subgrade stabilization if there is like soft subgrade conditions. The geosynthetics we use are these woven geosynthetics that claim to provide all three of these services. So they would give you the filtration and the separation that like a separate fabric would do, but also give you the reinforcement that a geogrid would do. These products are typically requested by the ODOT field divisions due to their help when it comes to constructability. Whenever you're building a road out wherever, Oklahoma, say you do all the earthwork and there's a massive rainfall event that comes in, you can delay the project by quite a bit just because of obviously you have to wait for everything to dry, you may have to rework the soil, all this stuff. What they've been doing is stabilizing the subgrade in areas where they allow that, and then using these fabrics basically as like a cover to basically protect the subgrade. Which all of this is great. I mean, it's good to use that, but there should be some sort of structural benefit to that as well when it comes to pavement design. Right now, we have it in our pavement design sections, but we're not actually using it as a structural, you're not able to reduce anything from that. So our goal is to be able to see what benefit you get from these products when it comes to a structural kind of ideal, and then be able to save money by thinning up the asphalt, potentially, likely reducing maybe the aggregate thickness, that kind of stuff. So this is an example of what kind of a pavement section looks like these days. We obviously have asphalt or concrete, and then you'll have your ag base, and then you have this geotextile reinforcement, which is these geosynthetic fabrics over stabilized subgrade. It's a lot. The actual structural calcs are mainly handled by the asphalt and the aggregate, and really everything below that is not really structurally being used. So going forward, we'd like to, since we're paying for it, obviously know all that it does and hopefully be able to get all the benefits out of it. So we just started this project with Dr. Atami where we're trying to develop a test method to quantify the structural benefits of geosynthetics so that a load reduction factor or a subgrade improvement factor may be developed. The idea, like I said, is obviously to be able to thin up these sections and be able to structurally apply it into either pavement ME or ASHTO 93 as you do your calcs. Determine field conditions that would benefit from these type of products. Like I showed you before, we currently are using it in situations where the subgrade is already stabilized. I don't know how much of a benefit you're getting whenever you have like a hard underlayer with these kind of fabrics. Obviously, you need kind of some sort of deflection for the fabrics to really provide like a structural benefit, but that's kind of what we're going to figure out from this research. Like, what situations does it make sense to use it? When do you actually need it for like a structural situation? And then obviously if they want to use it for their construction, that's fine, but I want to make sure that we know when we can actually apply it to the pavement design process. Potentially save money, like I said, that's always my number one goal with a lot of what I do, and then maximizing the benefits of the products the department's already paying for. So ODOT's already putting this on all their projects. Let's make sure we're getting everything out of them. All right, sorry. Okay, future goals. What is the new stuff coming up? So there's there's a million things to update with geotech. Like I said, we were kind of stuck in a certain way for a while. So a lot of the stuff we need to update. We are going to be looking at our geotech spec. That's basically our recipe book that we use for our geotech studies in the state. I'm going to be working with Scott. I'm going to be working with the designers, trying to figure out, what design parameters are actually needed for everything, making sure we're doing the right testing, making sure we're not doing too much testing. Another way to potentially save money. Just get that fine-tuned to where we can kind of move forward, being confident that we're doing the right thing. Pavement and Me, this is a big one. We were using Pavement and Me and AASHTO 93 kind of jointly, but like I said, we had brought consultants in to help us quite a bit, and the training that the consultants had for Pavement and Me was it wasn't great. So we were getting results from them that were inconsistent, not necessarily helpful. We're obviously paying them for this service, so at a point when you're paying somebody for something and you're not getting the results you want, you kind of take a step back. So we had the consultants go back to using just 93 AASHTO. We're still using Pavement and Me, but we are working towards actually making it more viable, more trusting. I would say the biggest issue Oklahoma has is trusting the program, because 93 AASHTO has this established, like, what you're getting. Like, we've seen roads built with it. They've been successfully lasted, the design life, all this stuff. Pavement and Me, it obviously thins things up a little bit, and a lot of the parameters we're using are national numbers, and I think it just building that level of confidence up is what we got to do. So a lot of that is local calibration, training, that kind of stuff. So we're hoping here in the next couple of years to have a Pavement and Me guide developed for the state. And I've been to a couple conferences where other states are doing this. They were even further behind we were. It's not an impossible task, but it does take time. So I'm thinking hopefully in the next 3, 4, 5 years, we'll have a process in place, and then it's something you have to keep on calibrating, keep on improving going forward. And then, so talking about digital delivery, so I'm a geotech. I would say digital delivery is something I would have never thought about unless I was at ODOT, but changing the format of how we deliver our data, that's gonna be a big thing, getting it to fit into a 3D model space, being able to use it for potential, excavation estimates, grading, all that kind of stuff, getting all that soil information into this model space is gonna be a big deal. How we're gonna do that, I have no idea yet. We have Katie that runs our digital delivery group. She's gonna hopefully tell me what she needs, and my job will be to figure out how to do that with the data. So that'll be a big one. I mean, that's a long-term kind of update that we're gonna be working on. Hopefully, if I come back in next year or the year after, I'll have updates on this kind of stuff too. So, like I said, this is my email. If you guys ever wanna have any ideas, geotech, research ideas, reach out to me. I can give you some feedback. I'll be happy to answer any questions if anyone has anything, for sure. So. Of course, yeah. All right. Well, anyway, my email's there, so. Sorry about that.
Just right. Great, thanks. Okay, our final speaker for the morning is Jeff Volz. So here's Jeff. Just one quick comment, as he and I actually, I don't know how far we go back, probably about 15 years. We knew each other 15, 20, yeah, we knew each other through a lot of ACI activities before either one of us came to Oklahoma, and I've admired his work over the years, so I'm sure you'll enjoy the next talk. Thank you.
Norb fails to mention that he's, of course, a UT Austin graduate. So after the Red River rivalry, I don't think we're friends anymore. Okay, so again, my name is Jeff Volz. I'm currently the Associate Dean for Partnerships in the Galilee College of Engineering. It's a role I just took on where I facilitate connections between industry and faculty. In my prior life, I had the pleasure of working on this project funded by the Oklahoma Department of Transportation, and had the pleasure of working with Gary Hook and Walt Peters, who most of you know are wonderful. And the title is Innovative Multi-Hazard Resistant Bridge columns for accelerated bridge constructions. I know that's a bit of a mouthful. So a couple of those terms, multi-hazard. So this column has the benefit of very high resilience and very high ductility. So a lot of our structures are subjected to seismic impact, particularly our bridge piers, thermal stresses as the temperature ranges increase, all of these multiple hazards that can impact our bridges. And accelerated bridge construction. I think we've all started to recognize that there is a huge benefit from having our construction projects, our transportation projects perhaps cost a little bit more in terms of direct costs, but get done faster because it has less impact on the traveling public and thus our economy, both for the state and for the country. So accelerated bridge construction is a big thing. So in terms of what I'll talk about today, I'm going to talk about the evolution of this concept. As most things, people have tried different things and the concept has evolved to where it is now. We started with hollow core concrete columns and then concrete filled tubes, and now the double tube concrete filled that I'll talk about today. There we go. And then in terms of our research project, our specimen design, fabrication, testing, our forensic investigation, and then thank yous, and if there's any time left, questions. I know I'm the last presenter before lunch, so you're probably not going to have any questions because you're hungry, but that's okay. So in terms of most of our bridge piers, most of the columns for our bridge piers are typically made out of reinforced concrete, typically circular, multiple piers supporting a pier cap. They can be rectangular or square. Sometimes you have the hammerhead shapes, but typically done out of concrete, cast in place. You have to build the formwork cage. You have to build the forms around it. You have to pour the concrete. And so there have been a lot of gains in terms of accelerated bridge constructions for bridge superstructures, but not as much for bridge substructures. We're still doing a lot the same, and that's the concept that I'm going to talk to you about today. So basically, we take a steel tube, we take a steel tube, and an FRP tube, and then we fill up the center with concrete. So we call it a double wall concrete filled tube. The benefit is that these different materials help each other. The FRP tube acts as a stay-in-place form. It also provides resistance to chlorides and other deleterious materials. The concrete core gives a lot of compressive strength, but also braces the FRP tube and the inner steel tube. And then the inner steel tube and the FRP tube provide confinement to the concrete, which increases its apparent strength. And then the steel provides the ductility and the flexural resistance for the column. You have no formwork. All the final structure is the actual formwork. You have no reinforcing cage to tie and install. You simply construct it rather quickly. So you pour your foundation. Typically, we do drilled shafts for a lot of our bridges. Put in your steel tube, get it in the right place, cast the concrete for the drilled shaft, come back and put the FRP tube on it, and then cast the concrete in the interstitial space between the steel tube and the concrete tube. And then you do that for all of your bridge columns, put the pier cap on, and you're done. So you could cast this column in a day. As soon as you put the steel tube in, cast the drilled shafts, come back the next day, throw the FRP tube on, cast the concrete in the middle, the column's done. So very rapid construction. But then the question is, how does it behave, right? As a structural engineer, I'm like, yeah, that looks a little, I don't know, right? Reinforced concrete, I'm very comfortable with. Steel, I'm very comfortable with. It's kind of new. As civil engineers, we tend to be a little conservative. So we had to look at it and how does it behave? So a lot of researchers have done some studies on this with different construction pieces. A lot of times there's with normal concrete, different sizes, different test methods, right? A lot of our equations take a lot of testing and a lot of proof before we're able to use them. But there are some initial sizing guidelines. You pick your outside diameter, which you can use typical column sizes that you use now to get started. And then you pick the concrete wall thickness is about 10% to 15% of the outside diameter. The tube thickness is based on subtracting the diameter of the FRP tube and the concrete to get to the steel. Steel thickness is somewhere between a 64th and a 32nd of an inch. And again, these are guidelines just to get started. Just like everybody knows, the structural engineers know that design is an iterative process. You don't know the answer till you know the answer. So some initial design guidelines help you get there quicker. And then the FRP tube thickness is based on whether you're in a low seismic area or a high seismic area, the compressive strength of the concrete, and the hoop tensile strength of the FRP. So this is our test specimen. It has a concrete base, you have the column, and then a loading stub at the top. Essentially, it's a flagpole that we're going to push back and forth with cyclic loading, which is kind of how our bridge columns work. So our column was 8 foot tall. The FRP diameter was, because of standard sizes, we want an 18-inch diameter column. It's about 18 5/8 of an inch. The tube thickness of 3/16, we went with the thinner value. The steel tube was 12 3/4 of an inch diameter, again, standard sizes, 1/4 inch thick. Again, we went with the thinner ones for these first set of specimens. And that gave us a concrete wall thickness of 2 3/4 of an inch, which is not a lot, but we'll talk about that in a minute. The FRP is glass fiber reinforced polymer, standards tubes, 40 KSI hoop stress. And then the steel tube has a yield strength of 52 KSI and an ultimate strength of 66 KSI. So we're going to put a nominal axial load on these specimens and then push them back and forth in a cyclic loading. We use high strength SCC, right? We want concrete that can flow very well to get into that 2 3/4 inch space. And again, if you have a concrete that flows very well, again, less labor involved. You just pour it in, you're done. You don't have to vibrate it. You don't have to do anything. So we use high strength SCC with a compressor strength at 28 days of 10 KSI. And we used our UHPC mix we developed at the University of Oklahoma with a target strength of 20 KSI. Technically, UHPC is 21.7, but we figured doubling the strength would work well. And both of those concretes flow very, very well. Tyler showed you how essentially UHPC is also a mortar, right? It's just sand and cement and water and high range water reducer. So it's a mortar with fibers in it. Now, because we only have a strong floor out at our lab on the south campus of University of Oklahoma, it's kind of hard to test a vertical column. So we developed a test frame so we could lay the column on its side and then test it. And these are the FRP tubes that came pre-cut, the steel tubes that came pre-cut, and then we built our specimens. And then a reinforcing cage for the base. So we built our formwork for the base, we put in a rebar cage, we put in our steel column at the right depth of embedment. Typically it's right now 1.6 times the diameter is the standard. Some of our research shows a little bit bigger value, but you want to make sure that steel tube doesn't pull out of your foundation. Cast the concrete for the base, remove the formwork, put on some strain gauges on the steel tube, slip the FRP tube over the outside, using spacers to get it in the right place. Put strain gauges on the FRP tube. And then cast the concrete. This is the high strength self-consolidating concrete, compressive strength of 10 KSI. No vibration required. Pores filled up the space very well. Again, this is about an 8 foot tall column using a chute from our concrete bucket. Flowed very well. After our forensic analysis, there were no voids in it at all. And again, there's no reinforcing cage inside that where the concrete is. And then we have the UHPC, which also flows very well. For those of you not familiar with UHPC, I know Tyler talked about his mortar was kind of like ketchup. I kind of look at UHP, it's like Nickelodeon slime. For any of those familiar with that green stuff, it kind of oozes out of your hand if you hold it, but it just flows forever. So it works really well in that very tight space. And then because we were having to lay the columns on their side and test them, develop our own test frame, we wanted to make sure that it would give us results that were valid. So we also cast a couple reinforced concrete columns, just standard circular reinforced concrete columns, spiral tie, that we could test initially, compare it to previous research, when there's a ton of research on reinforced concrete to make sure our test frame was indeed testing them in a valid way. I think this thing's possessed, by the way. Because we only have a 5-ton crane at Fears, with the loading head installed on the top, it would have weighed too much. So first we had to move it, we had to lay it over, get it in the test frame, and then cast the loading stub at the top. We applied our nominal axial load using pre-stressing. We just use axial pre-stressing, 4 half-inch diameter special strands, cast within the column that we would pre-stress to get our 80 kip axial load that will be constant during the cyclic testing. And that's what those white tubes are. So here's one of the frames, one of the specimens in the frame getting ready to test. You see the crimson frame here in the back. This is our base. We've anchored it with high strength rods. This is the column test specimen, the loading stub. These are the pre-stressing strand that apply the axial load. And then this is our hydraulic actuator. It's a push-pull actuator, so we could push it in each direction, then pull it back in the other direction. And then this is our 100 kip load cell. Our data acquisition system, you can just see these red wires. These goes to the strain gauges on the FRP tubes, on the concrete tube, or the steel tube. And then there are wire pots on the other side to measure the displacement of the columns. And I love my graduate students. When we first showed them we were going to test it that way, they're like, oh, that's not the way a column works. So the dead weight of the column is going to throw everything off. And I was like, no, we're putting 80,000 pounds on this. The dead weight of the column is like minuscule. So don't worry about it. It'll be fine. The loading protocol is based on a typical loading protocol for cyclic loading of columns. It's a FEMA guide where you start out with a small push and pull displacement-wise, and then each subsequent cycle you increase by 40%, and you do 2 cycles at each displacement. So this is a displacement-controlled test as opposed to a load-controlled test. So then we look at our plots, right? Engineers, we love plots. This is going to have displacement on the horizontal axis up to 15 inches, so the marks are 5, 10, 15. Load either compression, pushing out, or tension, pulling back on the column all the way up to 50 kips. And this is our typical hysteresis loop for a column tested with cyclic loading. This is our reinforced concrete column. So you see an initial linear elastic response, which again, we're going to push it off. We push it very slowly, very, very small amount in the beginning, but we keep increasing by 40%, so it increases pretty quickly. So you have initial linear elastic response, then the steel. You got a circular column, so the steel farthest on the outside on the compression and tension faces starts to yield a little bit. The concrete and compression starts to become slightly nonlinear. Because the concrete column is poured on top of the base, it's not integral with it. You have some bond there, but eventually you break the bond. You become more and more nonlinear. And then out here somewhere, we actually start buckling the longitudinal steel in the reinforced concrete column, and then eventually fracturing. And we got up to about 10 inches. So this is an 8-foot tall column that we wanted to push a foot in each direction. So that in one direction, that's a drift ratio of 12.5%, which is huge, right? 8-foot tall column moving a foot. If you saw that in a bridge, that would be kind of scary. We push it 1 foot, all the way up to 1 foot in both directions for the peak response. And we compared this with research on reinforced concrete columns. The behavior was very typical. So we felt like our test frame of loading, turning the column on its side and testing it worked very well. So we were ready to test our innovative columns. So this is for the column with the high strength SCC core. Again, you can see a nice linear elastic response in the beginning, and then eventually the concrete starts to become nonlinear in compression, right? Concrete becomes nonlinear at about 40% of its compressive strength. You start to yield the outside edges of the steel tube. The steel tube is the only thing embedded into the footing, right? The FRP tube stops at the top of the footing. It provides no longitudinal resistance. It mostly provides confinement for the concrete core, increasing its apparent strength and acting as formwork. So you start to yield the edges, the outside edges of the steel tube. You get more and more cycles, the displacement's getting bigger, you yield more of it and more of it. Eventually, you buckle the steel tube. Now, I talked about the fact that the concrete could brace the internal steel tube and the outside FRP tube to increase their buckling resistance, but it's only on one side. The steel tube can still buckle inward, but it can't buckle inward all at the same location because that would put it in compression hoop-wise. So it has to buckle in an odd shape, much different than if it was just a steel tube by itself. So you do increase the buckling resistance, but eventually that steel tube is going to buckle because you're at very, very high strain rates. But the interesting thing is the column still has a lot of post-buckling capacity. And what happens is you start to see this dip and then an increase in load. This is because when you're pushing in one direction, the part that's in compression, the steel tube buckles. When you pull it back and start pushing in the other direction, you straighten out that buckle, and then the steel tube starts to take more and more tension. So you get this very, very interesting behavior. And you can see there's some drop off in capacity. We had a peak here at about 3.5, 4 inches of 42, 43 kips. We're losing a little bit, but we get pretty close. So it stays fairly consistent. It has a lot of ductility and a lot of resilience, right? We're talking about pushing this column, an 8-foot tall column, pushing it 2 feet from 1 foot in one direction to 1 foot in the other direction. And then we stopped at close to 12 inches because our actuator didn't have any more stroke. And that was the end of the test. And then this is the exact same column, same steel, same FRP, but with the ultra high performance concrete on the inside. And you can see, we get that same linear elastic response. We start to yield the steel tube. Concrete starts to become nonlinear. We have that same kind of plateau, which all of a sudden we start to straighten out the steel tube when we're pushing it in the other direction. But the interesting thing is with the UHPC, you don't see a drop off, right? You see increasing load, till finally about here, when we're out at about 12 inches, we finally start losing capacity. So completely identical, a lot more resilience with the UHPC. And when we open it up, we'll talk about why that was. And then here's a comparison of the two. It's about a 17% difference. And that's mostly because of the confinement, the extra confinement that the UHPC provides. Not because necessarily of its compressive strength, but because of the small steel fibers that we put in the UHPC. And again, the important thing when we talk about durability, resilience, ductility, we all know that inside that hysteresis loop, there's energy being absorbed. That's why you want a nice, ductile response during an earthquake or a seismic event or an impact. Anything that puts a dynamic load on your columns, the fact that they can absorb energy makes them more resilient. So these are behaving very, very well. So then we opened up the columns. This is our concrete column. We zoom in a little. Typical response, some of the longitudinal bars have buckled. Some of them had fractured. This one has fractured and this one has fractured. So very typical behavior. So again, we did that to make sure that our test setup was accurate for when we tested our new columns, and everything looked really, really good. So then this is the one with the self-consolidating concrete, high strength. You can see looking down how much we're pushing it over with our actuator back and forth. This is close to failure for the column. You see the FRP tube, you see these white marks. This is the FRP tube starting to snap, the fibers in the FRP starting to snap, exceeding its hoop stress. Remember, it's providing confinement to the concrete, so it increases the apparent strength of the concrete, and it's starting to fail. And just kind of remember how far this comes up in terms of the failure of the FRP. And then we strip off the FRP, take the load off. We start looking at the concrete that started to crush in compression, started to pulverize. Typical for even a reinforced concrete column, the core was still keeping fairly strong. Again, no bond to the footing. And then we look at the steel tube. You can see how the steel tube is buckled. Actually, with the self-consolidating concrete, it actually fractured. So it was a low cycle fatigue where we fractured the steel tube. And again, looking down. And then this is one with the UHPC core. You can see near failure, there's not as much failure of the FRP because the UHPC is providing a lot of confinement because of the steel tube, the steel fibers inside of it. Then we opened up, it looks in really, really good condition. There were still some fractures, some cracking, and then removing the FRP, the UHPC, you can see the fracture. Oh, back up, back up, back up. It won't back up. There we go. So you can see the steel tube. With the UHPC, the steel tube buckled in a much more three-dimensional way because of the extra confinement of the UHPC, which increased its apparent strength. And we did not fracture the steel tube for the UHPC column, and we tested 2 identical specimens for each of them. And then looking down. And then this is a video of a test. It's a time-lapse photo, pushing it back and forth, just to give you a sense until you see it in person. We had Gary and Walt out during one of our tests to see it, and you see how much that we're pushing it, again, a foot in each direction, which is a huge for an 8-foot tall column. And yet the one with the UHPC, we could actually not fail. The one with the SCC did extremely well. So again, thank you to the University Oklahoma Department of Transportation for funding this project. It was a 2.5-year project. We had some match funding by the ABC UTC at Florida International. DeLisi, which provided a lot of our concrete materials, Grace Composites, which provided our FRP shells, and WW Steel provided all of that steel for our test frame, which was probably about $20,000. My co-PI, Dr. Floyd, and our graduate students and everybody else that helped out. So with that, questions? Did I leave any time at all? All right.
Please join me one more time in thanking all three of our speakers.